One of the earliest recorded observations of an astronomical phenomenon refers to the zodiacal light, which was described in the Quran, depicted by the ancient Aztecs, and mentioned by Aristotle. It is a faint glow in the sky at night caused by sunlight reflected off small dust particles in orbit around the sun. I'm Jerry Weinberg from the Dudley Observatory in Albany, New York. I have one of the 3 Skylab experiments at Dudley Observatory. My experiment is designed to measure the zodiacal light. The zodiacal light is shown in this painting here, depicted as this faint glow rising up from the lunar surface. This is the way it would appear to an astronaut in the command module. The lunar excursion module is shown here, descending to the lunar surface. The Earth is shown here, with Venus here, and the Sun several degrees beneath the horizon. The word zodiacal derives from zodiac, which is a band along the sky, positioned approximately here, along which the Sun, the Moon, and the planets move across the sky as seen from the Earth. The zodiacal light is concentrated along this band, and it is brightest toward it and toward the Sun. In our experiment on Skylab, which is called Gegenschein zodiacal light, and which has the number S073, we're going to be making measurements with a small telescope and camera of the brightness of this faint glow on the sky through all 3 Skylab missions. If one looks down on the solar system from above, and this is the Earth, the Sun here, and the Earth in orbit about the Sun, if you look in any direction from the Earth through the whole solar system, you'll see sunlight reflected back off any particles that are along this direction. For example, if I put a particle here, the sunlight strikes this particle and is reflected back toward the Earth. The same happens for all those particles along a particular direction. And this light that is reflected back is what is called zodiacal light and is what we'll measure in this experiment. The Gegenschein is another manifestation of the zodiacal light and is derived from the German word which means against glow or brightness. It is a brightening in the sky opposite the Sun from the Earth, so that if one looked in this direction away from the Sun, from the Earth, one would see that the sky would get darker here and then start to get brighter in this region. This brightening opposite the Sun from the Earth is the phenomenon called the Gegenschein. Our experiment will utilize the scientific airlock or opening in the spacecraft, and the astronaut will extend the instrument 18 feet out through the scientific airlock to where it is beyond these large solar panels, which are always directed toward the Sun. During part of the mission, we will also operate out another scientific airlock, which is just opposite the one toward the Sun. It will be facing out in this direction. Since the zodiacal light is not distributed uniformly over the sky, it is brighter near the Sun and other regions, we have to scan our telescope over the sky to make these measurements. We have control equipment within the spacecraft that the astronaut uses to program the instrument to be able to scan in different directions, in different ways, or to look in any one direction. This is the engineering unit of that experiment hardware that is now aboard the Skylab. It was developed by the NASA Marshall Space Flight Center, Martin Marietta Corporation, Denver, and the Dudley Observatory. Packed within this canister, when the instrument is not extended, is all the experiment equipment, including the extension mechanism. This end of the canister butts up against the scientific airlock. And on the front of it are several of the control panels which the astronaut uses to control the equipment. These 3 control panels are used by the astronaut to set up the various switches which operate the instrument to perform the various observing scans on the sky that we need. In particular, this box here is an automatic program which permits the astronaut to set up the switches and perform a program unattended after he has initiated the program start. The instrument is shown here extended its full 18 feet. It's supported by guide rails because in the lab we don't have a 0G condition weightlessness like we have in space. Similarly, this end, which contains the telescope and camera system, has a counterweight on it to balance it for operations that we do in the laboratory. When the instrument is extended from the scientific airlock, it points directly toward the Sun. Since the instrument was designed to look at very faint light that is a million times fainter than the sun, we have to point the instrument away from that direction by at least 15 degrees before we can start to make these measurements. To make this move, we can move it around the direction of extension and or away from the direction to the sun, such as it's now doing. The head, which is everything beyond this point, consists of two major systems: a telescope photometer system, which is shown here, and a camera system here. The telescope measures the light coming in from the sky, from stars, zodiacal light, and anything else, and converts it to an electrical signal back here, which is then sent back to the ground through the spacecraft telemetry system. The camera periodically takes photographs as the telescope is making regular scan measurements around the sky. The two cylinders at the end are sun shields, which block the direct light of the sun from falling on the objective and allow both instruments to observe to within approximately 15 degrees of the sun. The measurements that are made with the telescope are made at 10 different colors and measure the brightness and polarization characteristics of the zodiacal light and starlight, and these are then separated in analysis on the ground after the data is telemetered to Houston. This telescope photometer on the top here is an outgrowth and a follow-up to studies we conducted in Hawaii between 1961 and 68, and the system itself is essentially equivalent to an instrument we used all those years in Hawaii and to an instrument we're using there now. During the Skylab missions, we are coordinating observations from the ground with observations from the spacecraft, together with observations using a different instrument on the first Pioneer probe, which is now en route to Jupiter and will encounter Jupiter in December of this year. One of the things we're hoping to do, which can't be done from the ground, is to look to within 15 degrees of the sun. This isn't possible to do from the Earth's surface because of the competition from other sources of light in the Earth's atmosphere, and because the atmosphere absorbs some of this light. By looking to within 15 degrees and also looking at a number of colors, we're able to get information that is not otherwise attainable. From the data that we get back, we hope to analyze the detailed nature of the particles that give rise to the zodiacal light. For example, we want to know, are the dust particles which give rise to it coming from the asteroid belt? Are they a result of grinding up of collisions of different particles? Are they a remnant of the original cloud of gas and dust out of which the solar system evolved? Is the dust associated with comet tails, or is it associated with all of these? An analysis of these observations will tell us something about the current state of the dust in the solar system, which in turn will enable us to say something about the origin of it and something about the evolution of it. What will it be like thousands of years from now? One of the principal things it will also tell us is that what are the effects of light scattered off particles that are suspended in a large region of space. All of our knowledge about the atmospheres of planets, much of the Milky Way, the solar system dust, comets, asteroids, is derived from information obtained from light scattered off bodies such as this. We are able here to observe these things from outer space without the complications of the Earth's atmosphere and to derive a lot of information we could not otherwise get. It is directly applicable to problems like pollution in the Earth's atmosphere, which is also caused by light sources being reflected off different particles. For example, sunlight reflected off different gas and dust particles. So the information that we get from this experiment has a direct relationship to any things that have to do with light scattered off particles, whether it is in urban areas, whether it is in high altitudes near observatories, whether it is from a manned or unmanned spacecraft.